everybody. Welcome to our 24th meetup. It's an awesome moment. We have gone through almost 2 years of being in existence. And today is going to be one of a very cool meetup. Um, Today we're going to do a reverse engineering workshop with Salp. I will grab him here. Oh, there's
Good,
Barre, Salp. Say
good
hello.
afternoon.
Hello.
Evening.
Yeah, evening. It is evening. It is almost 6:45 already. I have a couple of notes before we get started. I actually wrote down the stuff so I do not forget it. Um, so yeah, well, welcome to this meetup. It is going to be awesome. We are going to have an awesome meetup today, but next month our meetup will be super awesome because we will be celebrating our 2 year anniversary. We have gone through 2 years of COVID stuff, and we are finally able to have a decent party. So after our meetup for today, I will open registration for the event next month, and that is very limited. It will be about 50 to 60 people, and that's yeah. So if you want to join in, be sure to register quite quickly. It will be awesome. We will have guests from Hack the Box coming over from Greece and England, hint, 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 and joining us in Utrecht to yeah, have our party. Um, for the rest, we do not know what we'll do, but there will be pizza, there will be drinks, and there will be cool people. So more than you could ever want. So yeah, Barre, what are we going to do today?
Plan for this evening is, well, it's labeled as a workshop on reverse engineering, but it's more gonna be a walk along with a introduction to reverse engineering. We're gonna briefly touch on how I roughly tackle reverse engineering CTFs and some of the underlying technology and techniques and tooling.
Yeah, very cool. Very cool. Before we start, the challenge that we will use is called You Can't See Me, I believe. Yeah,
Yes.
it's You Can't See Me. In the Discord, there is a password for the Capture the Flag platform by Hack the Box. It's ctf.hackthebox.com. In case you do not have VIP access, so you need to just grab it there. You can join the CTF called Netherlands Meetup, and the password I will magically put in the screen right now. This is a horrible thing to type in, so please just copy it from the from the Discord channel. But in case you can't do that, here it is. I'll leave it in the screen for a little bit. Yeah, so let's get it started, Bart. We
Okay.
have run through the evening quickly. Well, quickly. We had some discussion about it. We'll have a break somewhere
Halfway point.
halfway.
Yeah.
Up to then, it is possible to just follow along, learn how Bagger goes through the steps, and yeah, just make it an awesome evening. So, Bagger, I will share your screen.
Okay.
There you go.
I
And
even have presentation, but you know it's
yeah,
going to be great when there's a presentation.pdf. That
indeed, indeed, and it's all black. So there we go.
absolutely. Okay.
All right.
So thank you. Yeah, reverse engineering, small introduction, and let's get started. Let's start with a disclaimer. This is a really deep subject with a lot of rabbit holes, and we can't cover it in a couple of hours. So I will be briefly touching on things. I will be only covering parts of things, and I will totally skip over others. Yeah, that's the best I can do at this moment. It might be that some things go too fast or you don't understand, that's no problem at all. The goal of this session is to get you started, to have a starting point to learn or get you interested. If there's any questions, Discord, YouTube chat, poke me afterwards. The goals for this evening. I want to quickly show my approach to RE challenges. I want to show some static and dynamic analysis of binaries. I want to demo some RE tools or related tools, and give an intro to some underlying text and principles. Focus will be ELF binaries, Linux 64-bit, so skipping Windows 32-bit, other platforms. Tooling this evening, a few of the tools I'll be covering. Plain Kali Linux with Gitro SRE, IDAR3, Binary Ninja, WHEX editor, strace, ltrace, and GDB. It should be shared in Discord where you can get them, but they're also here. Then let's start. Who am I? I'm Barre, also known as Salp on Discord. I've been a software developer since '98 professionally. Don't work in IT security. And I've been doing capture the flag since October 21, so really recently. And I think I've been doing reverse engineering since December, so I'm also completely new to this field. The challenge we'll be tackling this evening is You Can't See Me. An easy challenge, it's retired, as mentioned before. Yeah, join along if you want it. And let's get started. Let's find a flag. So here you can download the file, and it also lists a SHA-256. I already downloaded it, and the password. What I normally do is I always, just as a double check, always make a check some of all the files I download, so I can see are they not corrupted, etc. I had it happen once where I had a corrupted file, and it cost me a lot of time. So I always run a check.
The font a little bit.
My apologies. I thought
that's a sentence. That's a sentence I say a lot during presentations. That's kind of my role.
Totally valid.
Can you make it a little bit bigger? There we go.
I thought I did, and I saved the preference, but apparently I didn't.
Computers. That's a horrible thing.
Or I might have reverted to a snapshot. I don't know. So let's start by unzipping the file, password, hack the box, and we end up with a file. What I do want to do during this presentation is at least keep some notes. One of the things I really noticed is note keeping helped me a lot in learning and also later reading back. I usually use Markdown. That's a personal preference. Cherry Tree, Obsidian, just text files, whatever works. So single file called out. The first step is, what are we actually looking at? Most basic command to see what kind of file you have is file. Standard Linux command. And it outputs a lot of stuff. So let's start dissecting that a bit. The file is a ELF64 LSB executable. Okay, let's start with ELF. ELF is executable in linkable format. It's a common standard for executable files, libraries, and things like core dumps. It's defined in something called a System V ABI. I will go back to that one later. And mostly used for Unix Linux systems for executables. We'll also cover what an ELF file consists of later on in the presentation. But let's first cover ABI. ABI, or Application Binary Interface, is a specification that describes the interaction between two binary programs, such as a kernel and a user program. And it covers a number of things. For example, the low-level structures and organization of things like stack, memory address, or basic data types like integer or short or character, and how they are padded, the endianness, and so forth. It also covers calling convention. How are methods called? So if you call a method, which arguments are placed on a register, which are placed in a stack, which registers are used for what, which registers are preserved between calls, and so forth. There's an API for actually every system. Windows has its own API, and there are various places to find it. I will link two of my favorites for the Linux API, including Wikipedia, in the Discord chat now. So that's ELF. Then 64-bit. 64-bit means this application is compiled for 64-bit systems or CPUs. And that also means it uses 64-bit instructions and 64-bit memory addresses. If you have a 32-bit program, it can work on a 64-bit system. Other way around, not an option. And okay, that's the really brief 64-bit. Then we have LSB. This is where it starts to get a bit more complex. LSB, or least significant bit, defines the byte order of, or endianness of 2 bytes of data and how it should be read, the order of how it should be read. Most common Intel CPUs, AMD CPUs, etc., all use LSB, or least significant bit. Networking uses MSB, most significant bit. And program files, it's up to the program. So it's all over the place. The SysV API does specify that executables should be LSB. Okay, to illustrate that, let's start with that. So if you have 2 bytes, let's start with a value that's bigger than 1 byte, 1 AA. That would translate binary to 1 for 1, 1010 for A, 1010 for A. If you would write it LSB, you would go 10, 10, 10, 10. No, I actually need to count.
While you count, can you increase the font a little bit?
Again,
see,
it's a disaster.
That's my role, see? Yeah.
Important role. I think the most important role.
Yeah. I'm just if I don't forget that I muted myself, then it is a very decent role as well.
True. So LSB, you would have, instead of the high number being first, like humans read, you actually put the high number in the second byte and the low numbers in the first byte. I will explain why later. First, I will show MSB as a comparison. MSB is also how humans read numbers. You first read the high number, the 1, and then the low number, AA or 101010. This has, why use LSB? That was, I think, the first time I came across it, I was like, why do this? What's the use? And this has everything to do with reading from memory in different sizes. This would be 2 bytes, or a short, or uint16, whatever you want to call it. If you would read 1 byte from memory, you would read the high byte, or the low byte, being 101010. If you would read 2 bytes, you would read the full value. But it changes the moment you start reading more bytes. 32-bit, or uint32, or integer. You start adding extra zeros at the back. While 64-bit or long, you start adding more zeros. In comparison, if you take MSB, and I'm just going to dump it all in one go, you start adding zeros to the front. This means that if you want to address, if you want the memory address of the number, you actually need to know the length. Where with LSB, the number always starts at the same place, at the same memory address. So you can easily read a 2-byte value as a 64-bit value. Really short on LSB, MSB. It's gonna be really important later. With a note, it's always LSB in binaries is always 2 bytes, and that has to do with how the CPU architecture works, which is 2 bytes complement calculation system that I'm not gonna cover now. That goes way too far into CPU design. So short introduction, LSB, MSB. I hope it somewhat clears it up. So what else do we have? Executable. We can execute a file. Okay, fair enough. Then from there, x86-64, that is, it's optimized for Intel, AMD 64-bit systems. Version 1 sysv, that's the ABI and the ELF version. We already briefly covered that one. It's dynamically linked. Basically, dynamically linked is there's a number of default libraries on the system, libc being one of the most famous ones. Or there's custom libraries that you bring yourself, or that the program has itself. You could either put everything in one file, which makes reading or loading the file really memory intensive and patching it nigh impossible. Or you can specify that my file uses these other binaries, .so files on Linux usually, and they contain the actual logic for certain function calls, and they are needed to run. So it's basically splitting up one executable into multiple executables. Then we have an interpreter, which is the interpreter of the system for executing the file, and LD is indeed linking related. It also covers all linking and access to the kernel. It's compiled for GNU Linux 3.2.0 and up, and it's stripped. Stripped means that all the information like function names, variable names, etc. are removed from the binary that were present in the source code. The other version is that the debug information is present. It takes up room and it's only usable for debugging or reverse engineering. Stripped makes it a bit harder to reverse engineer, but with a little bit of practice, it's really easy to overcome. Okay, so we know what kind of file it is. It's an executable. We can run it. We are running on a 64-bit Linux, so we should be good. It did say it was dynamically linked. I'm not, on purpose, not going to execute the file yet. I first want to see what are we even looking at. It's the same I also do with malware. I sometimes do reverse malware for fun. And immediately executing malware can be a painful situation. At least it requires a rollback of your VM.
That's so quite YOLO, right?
Oh, absolutely.
Just run it.
I've done it before. There was a certain Ukrainian Viper that was going around. I was really curious what it did, but I used a burner PC for that I was willing to trash. That one I actually YOLO'd, but in a really isolated environment. So we know it's dynamically linked, so we know it uses other libraries. Default Linux command LDD shows the libraries that it uses. And in this case, it's the Linux VDSO SO.1, which is the virtual dynamic shared object. The kernel reads the core part of your operating system and also the part where your root is a dangerous place for users to interact with. So there's a virtual dynamic shared object which exposes limited amounts of the kernel in a safe way, is the plan. Most of the time, 99% of the time, it's safe, but it really limits the access from a user program to the kernel. Then we have the libc, what we mentioned before. It's the standard C library, which contains things like printf, malloc, nec function, And we've got the before mentioned runtime environment. It's a linker shared object. Okay, so we don't see anything special here. You will see this with 99% of all Linux programs. Then first step of solving a challenge, a reverse engineering challenge, is just strings. It's the best command ever. I've solved a number of, especially easy ones, are really easy solvable with strings. Strings takes, there's a certain range in ASCII characters that are deemed human readable. And what you do is you specify a length. I think the default is 4, which produces a lot of garbage. I usually use a default of 8. It looks for a sequence of 8 characters that are human readable in a file. In this case, if we run it, we see our linker, libc start main, glibc, gmon start. Hey, and now we're seeing interesting things. We see a welcome. I said you can't see me. This is the password. Okay, we might be done. And some weird text that is present near the rest. So let's make a note of this one. We actually might already have the password.
Can you increase the font a little bit?
Yes, and I'm wondering why it reset. I did increase it before.
Yeah, I think maybe you open a different window.
No. I will keep an eye on it. Okay, so we have 2 possible passwords. 3. Welcome sounds like a welcome text. Don't think that's a password. This might be the password. It looks like the name of the challenge. This is the password. That would be that giveaway. And something strange. Yeah, could be a password. This is one way to look at the file. There's another way. That is xxd, which does a hex dump of a file, which shows the text, plus it shows the hex code and the position in the file. Easiest thing to do, it shows a whole executable with a lot of garbage. Easiest way to do with this is I always pipe it to less, so I can just scroll back and forth, and it gives you a search function. And we know that, for example, password was one of the words. And now I'm getting crazy.
It is probably wrapping around. So search for
okay.
Yeah.
Okay, let's. Yeah, it is wrapping.
Yeah.
Oh God. Yeah. So we can see here at position 2000 we have welcome. I said you can't see me. We had that one. We have another one, HTB, %s. That looks to me like a printf formatted string in C, but just in case, I'll add it to my possible passwords from binary. Then we have, this is the password, and we have a longer string. It's actually longer than the one we saw before. So it might be that this is actually not the full one that was picked up by strings, but strings cut it off because there was a character that it saw as a terminator. So at least we found something. Then you can scroll through the whole file. You will see a lot of null bytes. I will explain why later. But yeah, nothing else really interesting stands out. If you don't like XSD, you can always go to VI and then pipe to XSD with %! XSD. This is also why VI is way better than Emacs, no matter what Arjen says. No, just kidding. But more official version is WX Hex Editor, which literally does the same. It does give some more auto conversions. So if we go to byte 2000, we were at if it renders. Okay. Let's see why this is not picking up.
It's called the demo effect.
Yeah,
stuff
or it's
goes wrong.
searching in hex instead of text. That could also be the case. Yeah, it's called the demo effect. It we should be.
You
No,
scroll past it.
Yeah, I thought 2000, offset 2000. Do I even have the right file open? Is now the main question.
That looks better.
This looks better.
No, it's the same.
It's the same. Okay.
There we go. No, stop. Go up. There
Nope.
we go. No, that's.
This looks like a .text block.
Yeah.
That's okay. Spoiler. It's not normal to recognize that.
Here we go. Yeah.
Here, this looks like a data block. Yeah, here we go. If you, for example, here take the W, it's not just only a W. You also see the 8-bit value, 16-bit, 32-bit, etc. It does out conversion. W hex editor. Yeah. Some people prefer the visual version. I normally use XSD, but matter of preference. Okay, so I already mentioned something like a .text block, and we also have, if we look up, we have things like rela plt, rela din, dynamic .plt, .comment. Let's go into what they are. An ELF file, or an executable file, according to the ELF spec, consists of sections, or of a header, which describes the file, sections, which are blocks of information on the file that are static and that are loaded, and segments, which is runtime information for the file. Segments you hardly use unless you go into really harder challenges. Most of the time, sections contain the information that you want. There's a program called readelf that can give information about ELF files. In this case, I'm saying readelf --white, else it's going to maintain a 80 character screen limit. --, sections, show me the sections of this file. What it shows is 27 sections with all various names, an address, an offset, and a size. The address I will cover later when we go into memory. The offset is the place in the file, starting at byte 0, where in the file. So at byte 2000 hex, there's a section called raw data, and it has flags, flags being allocate or read, write, execute. Those are the most interesting flags. If you want to know all the sections, read up on L files. We can't cover them. The most important ones for us are .text, which contains the executable code of the file. The .text contains, okay, what do you do? Something I'm not going to cover now is reladin, relaplt, got plt, have everything to do with where functions are and which file, where in memory. But we're not going to cover that. And the two other ones are .data and .ro data. .data and .ro data, if you specify a static value, so for example, a string or a number in your source code and you use it directly, they are stored in the executable in these two sections, the .data, .ro data. And if we look here, offset 2000, that's also where we saw the welcome text, HTTP, this is a password, etc. We're going to skip on segments, but we can also use readelf to make sure that what we read, in this case, readelf --white hex dump for dumping the hex values of a section, .ro data, or read-only data, and hex dump for .data, for the out file, gives us just those sections with the values. And this is also this is where we can see that the texts we saw were indeed stored in the RO data. .data is empty. You will see that most of the time, because it's also a really dangerous section because it's writable. Writable sections means they can be overwritten. That's an interesting trick for binary exploitation or exploit development. Okay, so we know there's a file, we have some potential passwords. Let's just run it, see what it does. So, welcome, okay, that's the text we saw. If we enter something, it says, I said you can't see me, which is the other text we saw in the RO data section. Then let's try, if this is text that is used to print out, let's try this is the password. No other behavior, so I don't think it's it. And this one I'm actually going to copy paste and not going to retype. That's just too much. But yeah, let's give it a try. No, also not. Now we can do two things. We can continue our investigation, or we can go the, I wouldn't say lazy way. I would say one of the best ways for me is CyberChef. GHQ UK has an open source tool called CyberChef, and it's got a lot of tooling for data format changes, but also for encryption, decryption, decoding of data. And it has the best feature ever. You give the text, you drag magic to the recipe. You say intensive mode. Depth of 5 is usually if I have a short string, and it will throw everything at it. XORs, different character sets, switching UTF-8 to UTF-7, and the easiest way then to check if there's a password or a flag is just scroll, quickly browse through it. A simple XOR, which is used a lot in reversing challenges, is easily cracked this way. Without going any further, you could get a flag this way. There's nothing that really stands out to me. that flags or passwords have the tendency to be lead speak, single readable things, or semi-readable in this case.
And what makes it more difficult in this case is that you see that generally Hack the Box uses HTTP, curly brace, and then something. So you would look for
Yeah.
HTTP,
Yeah.
but we've seen in the text that it actually separates those two out. So
Yeah.
it is quite interesting.
Yeah. Well, still with the visual inspection, I've seen it happen more where they use HTTP and then separating it out. Oh, sorry. But with the visual inspection in CyberChef, at some point you'll start recognizing things, words with underscores, semi-readable, lead speak, or just normal text. But in this case, nothing stands out, so no luck. We could have solved it. But yeah, no, it's harder than a baby RE. I think that was strings that actually solved it.
Yeah. And it actually says strings is not the way. And,
I saw.
of course, it's the way.
And they actually lie in the description. They said 4 ways. I broke it in 5 ways. So originally I was planning on doing this one with Baby RE until I saw that you did the last presentation with Baby RE, and I find this one more interesting for the step we're taking now.
In the chat, CTFL has a very interesting observation. He says, "Notice that the 2 strings have the same length. Might have a XOR." Which is also
that's a really interesting observation. Yes. Yeah.
We'll get to that, I guess.
I didn't notice that they had this when I saw did a string dump or when I dumped it. I didn't notice it had the same length.
But that's also the beauty of taking good notes.
Yeah.
They have to you visually see that they have the same length.
It's a good thing to put in your notes as well.
Yeah. Richard now asks which 2 strings, but our YouTube channel is somewhat delayed compared to what so now he gets it. Yeah, there we go.
Yep. And it's a good thing to take notes of these things. You could go quite far with that. I could, after we're done with this presentation, I'll quickly show my notes that I took on this challenge. But I must say I did this challenge while talking with Kradamp to find a new challenge instead of Baby RE, since that one was already done. But okay, so no luck so far. Same length, XOR, no taken. Maybe it is. Other thing you can do. Let's see what the program actually does. There's 2 options. There's 2 ways to see what a program does in terms of calls outside itself. There's strace or system trace, which shows all the system calls the program makes via the kernel. And it's probably better to show and then explain. An strace. What it does is an exec VE. This is standard for every binary execution in Linux. There are some really nice exploits you can write with this if you keep this one in the back of your mind. But that's out of scope for now. It actually means replace an executable in memory with another executable. We can see it access a file, LDSO preload, a lot of memory map, close, open add. These are all files dealing directly with underlying system. And these are all system calls directly to the kernel. This until the point of let's see, where are we? Until this point, you will see something similar. Mapping of memory, protecting memory you will see something similar in every execution that you see. We see a write, welcome. That's indeed what we saw. And then we see a read, so it's waiting for input. What happens when we enter text? Okay, we see that it writes, it can't see me, so this doesn't give us anything. System calls can be really interesting while reversing to see what the program does, but it doesn't give us anything. There's also another, the S trace is for system calls. There's also L trace, which are the calls to the libraries that are loaded. So the shared libraries in this case. So let's see what that one gives us. We see a printf, libc printf for printing a text. We see a malloc, allocation of memory, 21 bytes. Then we see an fgets, reading the text. And then we see a string compare. Whoops, you did see me. Is compared to test. And then it says, I said you can't see me. Might is actually be the password. Let's try. And we have a flag. You can now submit it for 0 points because it's retired. But we're done.
On the capture the flag platform, you get 1,000 points for it.
I should join the capture the flag platform because I just got 0 points for it.
For imaginary points, if you want, right?
Those are the best. I mean,
Yes.
So, okay, we got a flag. We could call it, or we could see if what else we could have done. And let's start with debugging. I'm going to give a disclaimer. GDB is quite archaic in the commands. There are cheat sheets online. I think a couple of universities have really good cheat sheets with the commands. Print them out, put them next to your keyboard when you start using it. Keep them in hand when you've been using it longer. I still have one nearby. And I've been mainly using GDB. It is the GNU debugger. It's a really strong tool, and it has some really nice plugins. Peda, Gef, Pwn debug being the main ones that allow you to that really add functionality for mostly exploit development or easy debugging, but mostly exploit development. So GDB, you can start it. You could say GDB auth. In this case, I'm just starting GDB, and I'm saying file auth, reading symbols. No debugging symbols found in .auth, which was also what we saw. It was a strict file. And then in this case, we're running it without command line arguments. So R run, and it's running the program. Starting program, welcome, Control Z or 6 stop, pauses the program, puts it in a stop state, and GDB takes over control of the memory regions, execution stack, etc. And I will cover those later. First step, what I always do is, what's the program doing? Backtrace or BT shows all the calls that are made from functions to functions to functions. In the currently executing on the top, there's a function question mark, a strip name that calls libc start main, that calls question mark. Given that it's an alpha, I know this is our main function, but that name has been stripped. The memory address also gives it away, but we'll cover that one later. That one calls an fgets. That one calls a IO getLine info, blah, 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 all the way to libc read, which is where it's currently waiting. So we now know what's being called, where we are in the program, in this place. And if you look at this address, this is also the address that, and I'm actually gonna zoom in because I remember.
I was just gonna say that.
I know. If we look at the file, this was the file offset, so the actual byte in the file. Hex 2000 was the actual byte in the file. And the text section contained our code, which 401070 is in line with, or is nearby where we are. So there is an overlap there. That also means that these addresses are corresponding to these. Okay, so
The thing that I always also indicate is that if you look at all the other functions, their address, they start with 7FFFFF. And so they are library space,
yes,
shared libraries that are loaded. So only
yes,
the
with a
40.
minor. Sorry, go on.
No, go ahead.
With a minor note that 7FFFF is only for 64-bit.
True. But we were looking at 64-bit.
Yeah. In 32-bit, you will see another address space. And okay, in 64-bit, this works. I'm not going to talk about memory address randomization.
We only have a couple of hours tonight, right?
Yeah, I was thinking ASLR and stuff like that. We're not going to do that. Okay, so we know where we are. Then we can also, and now we're going to get a bit to the archaic GDB, examine, and then a slash X for examine, because that's logical. And then a slash, and then the number of things you want to print, and then what you want, how do you want to print it. So we were at this memory address. That's our main function. We can deduce. libc start main always calls the main function of the program, the user main function. So at this address, what's going to happen? And this is, we can print it out. We can just say OX at this address, 8 instructions. I would suggest, given that it already went all over the place in a lot of theory, I'm going to give a really brief introduction to assembly and memory after this. So I would suggest a small pause for people just to grab a coffee, etc., because it's going to go fast and deep from here on.
Yeah, we can do that. I have a question, though.
Yeah, of course.
I personally really like using Jeff together with GDB.
Yep.
Because it also gives a code listing of where we are. It shows the stack and all these type of things. Do you have any preference to a extension to GDB, or are you a GDB purist?
It really depends on my mood. Like I said, I haven't been reversing that long. It really depends. I also use a reversing tool for the runtime, for debugging, like Binary Ninja. I use Pwn debug more than Jeff. And I also sometimes go pure GDB and split it. There are layouts in GDB that do the same as Jeff, that also show your registers, that also show your assembly in a second pane. Yeah. It really depends on my mood. I haven't done this long enough to really get a preference.
Yeah, okay.
And in this case, I'm going pure GDB because then, why Jeff over Peda over Bone
Sure.
Debug?
We get into a religious discussion that you started already with editors. So yeah.
Oh, not my fault
Oh,
that you prefer Emacs.
somebody has to be the right one. There's now there's CTFL on Discord
Yep.
also has a question. It says there's some very useful commands in GDB like info and help.
Yes,
For
and I
so
will show
info
them.
functions. Yeah, we will cover those. So
But I
we will.
first want to explain what we're looking at and
Yes.
explain what the different types of memory are and what registers are, etc. Before we go into that. So,
Yeah, there's some remarks about being rookies. Everybody is a rookie until they ascend, and then they are no longer. Uh,
yep.
So yeah,
And I see a remark. What did I do to learn all these things since December? Well, I did program assembly in the early 90s. I've been programming since the late 80s, so that might help. And I always have a masochistic streak of wanting to know how things work. For example, I've programmed Java for, I don't know, 20 years. And I can also tell you how the garbage collector works and how bytecode in Java looks like. And I want to know how things work. That's also what my um, security and CTFs have always drawn to me, but never got to it. I want to understand how I could also explain it. Basically, for simple processors, I can explain it on an electronic level. I can on an electrical level of pulses.
yeah. You have the tendency to go very deep on a technical subject.
And
You want to
yeah,
figure out how everything works.
yes.
Yeah.
For those following along in Discord, I was reading some 60s papers yesterday on software development.
Yeah,
But
but there's another question. It says, well, any recommendations on CTF sites? We obviously have Hack the Box. It has a limited set of challenges.
personal preference. If you go hack the box, try hack me. I personally like going in deep. Hack the box gives you a playground where you have to find your own way. It gives you less hints. In the beginning, it gives you hints. But yeah, it counts on you searching, asking, reading. Where Try Hack Me really explains and takes you along step by step. So that's a really personal take on how you learn. For me, Hack the Box is absolutely the way to go. Try Hack Me, I tried a couple of things and it felt for me like a checkbox. But I know that for others it can really work. There's things like PhoneHub. If you where VMs of varying quality are posted.
Yeah, that's
There's
now OffSec, right? They have
yeah. Okay.
they bought it. Yeah.
Okay, I didn't know.
Yeah.
But,
I personally also like rootme.org, which is a French website, and some students will know. Bienvenue dans le challenge de cracking.
okay. There's also things like over the wire
Yes.
and under the wire, which are more specialized. Then you have the. I'm thinking where. No, I'm actually.
Now you need to know
The
what
Phoenix
it is.
crypto challenges. Where were they?
Yes.
The Phoenix ones. Where were they from? Exploit something.
Yeah, I don't know. I don't remember.
And there's really, but it's an old one, but it's actually really good. Exploit education. Exploit.education.
Yeah, it's already in the chat indeed.
Okay,
Yeah.
Exploit.education is actually good. I like it. and it's mostly focused on reversing and binary exploitation. And I actually use malware, live malware, for reversing. And then you're going to go things like VX Underground with one of the biggest collections freely available. Mind you, do make sure that you know how to set up a lab. And in some cases, if you don't know what it is, or if there's some big disclaimers when you get it, I use burner hardware. I actually use hardware that I'm willing to really trash. Yeah.
Yeah, that's the life of doing interesting things, right?
I don't know if it's interesting or just stupid. I'll let you know later.
Yeah. Shall we continue? So
Yes, let's
people
continue.
have had the time to catch up. There is some discussion on where to learn things. So up to now, we've done some static analysis of the file. We looked at file, we looked at sections, we looked at string data. Then we did some dynamic analysis with strace and ltrace.
Yep.
And with ltrace, we found the password. So we actually finished the challenge. But like you, I like to try different ways of solving this one. So I don't know if I should already say how long it took me to do this challenge. I don't think there was any
there were no takers.
There weren't any takers.
Shall I start first, and then you can top me?
Okay, sure. Why not?
Now, I think I took 40 seconds. I think I was chatting with you, and it took around 40 seconds. I was looking for a new reversing challenge. Yeah, 40 seconds.
Yeah.
Your turn.
He asked me, yeah, you do it. So I did, and 13 seconds later, I had a flag.
Yeah.
But that's simply because there's a process that you follow, and especially with easy challenges, it can never be too hard. But then the interesting thing becomes, how does it work, and are there more ways to do it? And GDB is one of them.
Yep.
And so we end up with this this overview of AT&T assembly.
Yes, and why I will explain that Intel assembly is nicer to read. And as a side note, your 13 versus my 40, where's the difference? I actually did a strings, and I actually tried out the two passwords. That's where I lost my time. But these kind of challenges, if you're used to it, you can do this seconds, literally. Okay, debugging with GDB. So
shall I do a quick anecdote about being fast?
Be my guest.
We at the meetup, we at one time had a CTF. I think it was quite in the beginning, and we had our friend Pink Draconian, who was presenting last month, and he dropped in like 20 minutes before the CTF closed. They thought, oh, nice, I will participate. And he ended up like being number 2 or 3. Taking everything, because he just went like blazing fast, and that's all experience and having a good methodology.
Yeah, and it's also, for me, what I recognize, especially being a new CTF player, I really draw on my experience as a developer and DevOps. I forget about the most simple things. I would not easily throw a password list at something. I would always look at the software first, which actually bit me in the ass in an actual CTF. Where I would always look at protocol, APIs, functional flaws, configuration flaws, because that's what I'm used to looking at. But yeah, you can solve so much with that. And then at some point you just start recognizing things that even without CTF or offensive security experience, you can solve a lot of things. You can be quite quick.
True story.
Okay.
All right.
Assembly. Let's start the fun. So, we ended up with, okay, we know this is our main function. What are we actually doing? What we have here is, like Gretham said, AT&T assembly. It's a notational style for assembly that is actually the most used one on Linux. And the other style is Intel assembly. And you can check it with show disassembly flavor. You can see the disassembly flavor is ATT. There's personally, I always use Intel, which has a different annotation, and I will quickly explain some differences in a bit after I printed out this one as well. This is the same instructions, but then as Intel. Main differences: ATT prefixes registers. I'll cover what those are later. With the percent, it's direct values or prefix with a string. And the order, where Intel assembly says, I want to put this in this. So ATT assembly says, put this in this, which actually makes more sense. There's also, you see braces here and square braces here, or square brackets. And the main important reason for me why I can't get used to ATT assembly is how memory is calculated, memory offsets. Here you see minus OX20 percent RBP. You see RBP minus OX20. Both are readable in this case. There's only an exception, and that is where I really struggle with ATT and will always switch. If you have the Intel assembly, I actually prepared one, address calculation, this RBP plus REX times 1 minus O or minus hex 20, which is a simple calculus. This is the ATT version. There are rules on what are multiplications and additions, but I always forget them. I don't know what multiplications are, additions. I just give up and switch to Intel. Only reason I use Intel assembly over ATT assembly, but the most important one. So default Linux ATT. So if you want to have same memory calculations, set this assembly flavor Intel. Just personal taste, but I just can't get used to ATT.
I think the Intel version is the most sane one.
Agreed.
From a beginner perspective, reading it makes more sense to say like, oh, do something with this. And what do you do with it? Well, the thing on the other side that either goes into it or you add it to it or stuff like that.
The only non-logical thing in Intel is you have your target as first parameter or as first argument in your source. So where you put it in goes first. What goes in second is, for me, counterintuitive from a programmer point of view, where I find it put this in that. That's my only remark about Intel assembly, where I don't find it immediately intuitive. Then assembly. Let's do a really brief introduction. I'm not going to go really deep, because then we'll be here tomorrow or next week or the week after. But I do want to give an introduction. So CPUs are programmed with a set of instructions. They are actually baked into the CPU. These instructions have various names, but opcodes, binary code, instruction code are common names for it. And the executable part of the ELF file, when we did a hex dump, that I at some point said, oh, this is a .txt section, had a lot of garbage in it. Those were actually CPU instructions, literal CPU instructions. They're sent by the operating system to the CPU, which in turn execute them and does all the things with the other hardware in your machine. And you could program in opcodes, but it's not really human readable. It's tricky in a sense that two sequences of bytes, one 4 bytes long, one 5 byte long, looking the same, can actually have completely different meaning. And there's also a minor thing I downloaded for fun and giggles. This is one of the most important documents if you are reading assembly and don't know what you're reading. This is the Intel 64 and 32 bits developer manual, volume 2. To give an indication, it's 2300 pages. And this contains every instruction on the Intel CPU and also AMD, including all the opcodes. OF47 is a C move, a conditional move to a 16-bit register. I use it. There are really a lot of assembly commands, and some are really fringe. I use it to look up commands. What does this even do when looking at assembly? Bound move, store extended bounds using address translation. I can't even remember ever seeing this one. I mean, it is a valid instruction. So this document is A, the reason why people don't write binary, and B, it's a really, really important document if you're reading assembly for the first time or into assembly. And I will link it in the chat. Okay, so common consensus was binary, opcodes, not readable. So the next step is assembly as a language. Assembly is a collection of statements that either directly translate from a semi-human readable statement as mov, call, GE, CMP to an opcode, or is something called a macro, which is a statement consisting of multiple statements that literally translate into opcodes. So this is, in terms of programming, the closest you will ever get to machine code that's still human readable. Assembly is, in that sense, a second generation, qualified as second generation language. It's the lower the number, the lower the abstraction. Third generation languages are C, Java, etc. Fourth generation, I think the most well-known example is SQL. And no, I'm losing my train of thought. So assembly. Most assembly statements deal with accessing memory or data transfer, arithmetic, or logical instructions. And there's also a fourth group that deals with interrupts, which is basically signals to a CPU that says, stop what you're doing, this happened. And that can be a key being pressed, a byte being flushed to a hard drive, whatever internal or external thing. But we're going to skip that one. So we have assembly for accessing memory, manipulating memory, data transfer, so memory, arithmetic, logical instructions. The data transfer instructions deal with writing to memory or moving values around. So, for example, LEA, or load effective address, or a move. Let's take into assembly. In this case, it would move this value into this memory. What that memory is, I will cover in a sec. Other well-known things are push for stack operations, pop. And then we have arithmetic instructions, which are basically arithmetic: add, subtract, multiply. But also bitwise instructions like XOR. Arjen mentioned that one in the last presentation, as CTFs usually use, and it was already mentioned also in the Discord. Can't remember by who, my apologies. And things like AND or shift right, or so those deal with actual manipulation of the data. And then you have logical instructions which deal with how the program flows. There are things like comparisons, like CMP, or test, or stuff like that. There are calling functions, in this case call, which says go do this function somewhere else and then come back to the execution where I am now. Then you have also jumps, which are go somewhere else with your execution, and these can be conditional. In this case, this is a jump equals. And that looks at the statement before, or not completely. I will cover how it looks later, and says, okay, if this is equal, then go to this, to the instruction at this memory address. Else, continue, etc. Those are the main things. There are a lot of, I'm already seeing some assembly guides being posted, an x86 instruction set reference in Discord.
I added it takes the mnemonics and explains, or the ops, and it explains what it does, what registers it influences, and what flags it influences. It's quite nice.
Yeah, I will also, after this, link some of my references that I usually use. I have a number that I use as well for quick lookups. So, yep, the basic assembly. Then memory. It all had to do with memory, at least the first part. Data transfer. And also logical flows had to do with memory. Go to instruction at this address. And then there's things like RBP, REX, RDI, and whatnot. Okay, I'm going to give an even briefer introduction to memory. And I'm going to do a really brief introduction on Intel family-specific memory. Else we're going to go into a whole different state. Everything in a computer is stored in some sort of memory. The code we execute is stored in memory. The data it's executed on is stored in memory. And the main memory types we deal with are, while reversing, are registers, stack, and heap. Let's start with stack. The stack is a reserved linear piece of memory that acts like a container. You can put things on the top, and you can take the top one out. And if you put something else in, it will go on top again. And if you say, give me a value, it will take the top value and give it. You do that with push, which puts a value on top of the stack. And you can take it off again with pop. The stack is used for primarily for arguments. It's quite small. Arguments, direct values like integers, and instructions sometimes, but let's park that one.
Local variables.
local variables is indeed, the low-level type local variables. A string, for example, will be a pointer, or a text would be a pointer on the stack, where a number is placed on the stack, like an integer. Then pointers is literally an address, like here, that says go look there, and that usually points to the heap. The heap is a block of memory. It's managed, and it's for you, the executing program, and it stores things like global variables, large data, text is or things where the size is not knowable, like text. With C, if you look at C programming language, if you do a malloc, you allocate a portion of heap. It's the big bucket or big sea of data. It can be fractured. It can be split up. Then we have the last group, registers. Registers are a special kind of sort of memory. They are small pieces of memory of a certain size that are on the CPU, and they have either a specific meaning or a general purpose. The available registers are, given that they're on the CPU, are also determined by the CPU vendors. There's a common set one, the x86 family ones. And Intel, for example, has a number of CPU registers that AMD doesn't have, and vice versa. So they are literally little pieces of memory on the CPU and specified on it. Registers are what the registers do is specified by the system ABI, or how they are used. I can't play the kitty game. My kittens are downstairs. It's a shame. So the ABI, so the system specification that also, for example, described ELF files, or the Windows ABI, describe what registers are used for what. The main ones we use are RBP. This is also what you see here, which is the base pointer of the stack. This is where the stack starts. Then we have a stack pointer, which will RSP, which will always point to the top of the stack. Then we have RIP, which is the instruction pointer, which points to the current instruction that's executed. Then we have a special one called eFlags, which is a control register. It's not a single value register. It's a collection of bit flags, so they can be on or off. And they store things like results, extra information on results of comparisons or arithmetic operations. Things like that or examples of that are the carry flag or the zero flag. Zero flag mostly used in comparisons, or the sign flag, whether a number is positive or negative. And there are a number of other ones. You can actually manipulate them during debugging. We're not going to do that this time. Due to them using the printf, we can't fake the comparison. A lot of CTFs you can actually fake a comparison, either by changing the binary or by setting a flag. Next time, more visuals on stack, heap, and registers. Okay, So you can influence comparisons, etc., debug with flags. Then there's a number of registers that are called general purpose registers, REX, RCX, RTX, R8 to R11, which are just put something in it. And there's two general purpose ones, RSI and RDI. And the system v ABI says these are the first two arguments for a function call. Knowing that, let's continue debugging. So we know that there's a string compare. We can see there's a string compare called at this memory address. That is not where we are at the moment. We are now at 401235. So that's from here. What you can do in GDB is set a breakpoint, which means once you hit this condition, in this case, once you are at memory address here, before you execute it, but after the statement before, break. Like we press Ctrl Z for 6 stop, it actually stops itself and gives control back to us. So let's see what it does. Okay, continue. 6 stop is always annoying. You might have to continue twice. Now it's waiting for input still. Okay, let's test. Breakpoint hit. Okay, so we're back in control. First thing I want to do is see where we are in execution. And now I'm looking why it's not picking my buffer. Well, also I do by hand. I want to see 8 executions. We know about an RIP register, which is our current instruction pointer. Let's go 8 bytes back. And then give us 8 instructions. So we see with an arrow, we're at the call. And everything until that point is executed, nothing here is executed yet. We also know from the that RSI and RDI contain the first two arguments for a function call. In this case, string compare takes 2 arguments. So let's examine string RSI as an argument, which is test, the value we put in, RDI, hey, there's our flag, or our password in this case. We can now continue. There was also a remark that could you show 2 other helpful commands in GDB. First one being help. Best command ever. You can also do help stack. It gives pages and pages of there are pages and pages of help available. The other one, if you, for example, want to know at this point where we are, at this breakpoint, what is the value of all the registers, you could do an info registers, and you can see RDI, RSI, and so forth. So this would have been another way to catch the flag. Debugging, just following along. There is a visual debugger, EDB. I have no experience with it. Apparently it's okay. But I haven't used it myself. I know it exists. Okay. So debugging. We ran the program, we manipulated the program. Or then we have the classic form of reverse engineering. In this case, disassembly and decompilation. Going from the binary code to assembly is called disassembly. There's also going from that to a semi-human or to a human readable format that looks like C or something else.
Yeah, I just call it pseudocode.
Yeah, it's pseudocode. It's called decompilation, and I will show that. And with this, we can actually take the whole program apart and see what it actually does, because we know about values, we know about, but we still haven't seen how it gets the password. Ghidra SRE, NSA, I think it's was it now 3 or 6 years ago? It just said his birthday. 3, I think 6. 3.
Yeah, it's 2019, I believe. So
Okay.
3 years.
Yeah. So 3 years ago, open sourced by the NSA after I don't know how long internal development. It's actually a really good tool. It's open source. It's free. It comes with both a decompiler and a disassembler, and I like it. It's Java. You can write plugins. It's quite active. It was vulnerable for Log4j.
Yeah, that's right. Yeah. And
That was fun.
since version 10, it has a debugger, or actually it wraps GDB.
It
So
actually
you,
okay. I haven't tried that one yet. So Gidra, you need a project because that's important. Non-shared, else you need a server. You can't just have a local GitLab. He says from experience. You need a project name. Hack de wereld. And you get an entry project. In that, you can start importing files. In this case, we want our all file with I. You say import file. You can also somewhere probably import file. I. Okay. Select the file, and it will say, okay, oh, I see it's an L file, little endian, 64-bit, GCC compiled. I'm not going to go into the options. And we press OK. It gives us some more info. And we now have a file. If we double click this, it will open up the actual tool. And the first thing it will say is it's not been analyzed. Should we analyze it? Default options 90% of the time are okay. Some rare cases, especially with CTFs, you might want to tweak those because, yeah, CTFs have a tendency to sometimes look for the most weird things they can do within specifications or outside of specifications. I still haven't finished bombs landed, but I know the trick that they do, and they misuse elf hard. Kidra didn't like it. Then you really want to start playing with it. So what we have is a number of things. Program tree, these are the elf segments or the elf sections we saw before. Dot text is where program code lives. You have a symbol tree, but these are the functions it could extract with brilliant names. This is, we're missing our debug information, so yeah, it just names it function address. And data type managers, import exports. This case, not interesting. So we're looking for a main function. It's stripped, so we don't know. But every file has an entry. Entry, that's the function that's being called. And this here, we can see our decompilation, which we could read the assembly.
could you increase the font a little bit?
Oh, that might be a thing. Two options. Display.
It's actually horrible when it comes to setting the font, but yeah.
Yeah.
There we go.
Let's see. 18. Is this readable?
Let's go to 22.
22. Okay. 22. Apply. And now it becomes really annoying.
Now you need to do the code browser as well.
Yes. Where can I find that
Yeah,
one?
there we go. Stop. Font. Almost. Yeah.
Oh, yep.
Yeah, it's very intuitive. It's the same layout.
Yes.
It's made by several different people within NSA. Right?
Designed by committee, absolutely showing. Let's be clear. libc start main. So we're in an entry function. I hope people can read it now.
Yeah, it should be good now. Should be good.
I'm sorry, program trees, simple trees, not readable. We're not going to use it from that one. So we have an entry function. So this is where elf says, okay, when you start, go here. Has stuff, don't know, don't care. libc start main. That's a libc based program. Don't tell me it did. That's interesting.
You misclicked.
Did I? Oh, yeah. Sorry. I opened libc start main instead of the first argument. libc start main is a libc start the main function, or the void main in C. And first argument is your main function. Working with reverse engineering tools. Most of the time, you will be spending trying to give things a logical name, because we have a lot of local fun data. I don't know what. It's not so much a problem in this one. We could actually extract it without going any further. But especially in more complex codes, it's not doable. And most of the time, you're just trying to figure out, what does this function do? What should I name it to make it readable again? Or what does this variable do? How should I name it? In this case, that fun something, it's main. We could change the argument. Undefined 4 means 4 byte. I don't know what it is. Well, I do. In this case, we can say the return type is a uint 32 underscore t. Go away. So this is, in the end, our whole program. We can see here stuff. We see a malloc. We see a printf with welcome. That was the first thing we saw. Then we saw in our ltrace a malloc of 21 bytes, OX15. In Ghidra, you can say, if you right-click a value, you can say I want it in octal, in decimal, binary. In this case, decimal, 21 bytes. And then we see an fgets of 21 bytes from standard in. And our string compare with based on the result, giving one of the two printfs. One of the first things in more complex programs I do, and I usually don't do in Ghidra, but I will show other tools I use, is, it's the function graph, not the function call tree. The function call graph shows, entry, what's being called by what. These are the entry calls main calls printf, fgets, string compare, malloc. That's what I usually do to quickly check, what's being called. Don't know how, don't know what. And then the other one is the function graph. This is, what you see here is your assembly. And I don't know if this is readable, but doesn't really matter. And every jump or every control flow statement, so a jump or an if or something like that, it will actually put it in a different block. Here you can really quickly see, what's happening. And then you start seeing things like, it goes here and it goes back. This must be a loop for sure. It has two options here. Either goes left or right. This is an if statement. And those are structures you start recognizing, and that really help in understanding what a program does. So let's start renaming a few things to see what actually happens with this program. So, these are all local variables, We see some weird value. If you mouse over, you will see different representations. In this case, underscore SI underscore SIHT. If you reverse that, oh wait, little endian, not big endian. Then this is, and what would be the next one? The password. And this is where endianness, etc., really starts mattering. To think about that. So, okay, but where's that value coming from? This is where we can look at. Yeah, you said 22, but I'm losing space here. This is also one of the reasons I have a 34-inch ultra-wide monitor. That in programming.
Let me teach you something about Ghidra then. Do you see
Yes.
the toolbar on the top of this sub window? There's a fourth button that is the edit the listing fields. If you click that, you get this
Yes.
overview. And then you see the operands
I don't
fields.
care about the address.
Yeah, and then you can drag it to become longer. So the operands fields that you're in now.
That's
Voila.
okay. I didn't know that one. I learned something really quickly.
There
Thank you for
is a
that.
book called the Ghidra book, which I actually bought, and it is so much better than the manual. The manual is really good, but it's so large, and the Ghidra book
Yes.
taught me this, and then I was very happy.
It was actually on sale on Humble Bundle last month, and
Yeah.
in the bundle, and I picked it up. I just haven't read it yet. I mean,
My life is now complete. I have also taught Richard something.
but I mean, next to me, I have this
Yeah.
one, and
Beautiful.
underneath that one, there's this one.
Yeah, and I will put you in screen now because people cannot see.
Okay.
There we go.
So, I mean, this is next to me, the Practical Reverse Engineering book and the Malware Analyst Cookbook. These are
very good.
two reverse engineering books that are lying next to me, and the reason why I haven't read a lot of books lately.
Those count, but at least
No,
I've
those
taught you
do
something.
count.
Yeah. And
That's
if you now
no.
click the button again, the top thingy goes away.
Yeah,
and then
nice.
And then you can just continue.
Yeah.
How beautiful is that?
So we have our decompilation, which has this value. If we look at the assembly, we actually see it goes to s underscore this is a password underscore this, which is a value in the .ro data section to the string. And so we know that local 28, which is stack base pointer or BS minus 28, local 20 and local 18 is actually one variable of 20 bytes long of the type char. So, I don't know, let's do this. It's a char array. You can also see it's immediately changes this to a single variable. And as mentioned before, the other variable is just the same size. And yeah, we must be getting our thing somewhere. So 48 till 38, we can safely assume it's a 20 byte character array. If we do that, there's values being put in. If you look at what it is, it's dot something which corresponds, if my mouse over is being picked up, with the values we saw. So this is the fake password, and this would be our real password, but then somehow encrypted. We also still see a malloc, memory allocation of a character array, type underscore with the name underscore s. It's used as an fgets, so that would be our user inputs. Suddenly, if you look at the string compare, it compares the fake password with the user input. How does it do that? for some variable is smaller than 20. Okay, so let's call this I, because iterate, this is a standard for loop. For I is 0, I is smaller than 20, I is I plus 1. So iterate 20 times over the thing. And it takes the real password and it adds plus n. In this case, we might actually want to know decimal value instead of new line, because we didn't see a new line. So it takes the value of the real password, adds 10, and then writes it to the fake password. We change this to pass with the result. Oh, that's data type. It should be. The shortcut I use is L for change name, Control L for change data type. That's why I don't use my mouse, but you can change it here. What we now see is it's a ROT10, literally a ROT10 cipher that they use. So they add 10 to every value, override the fake password. That's also why we couldn't see it in the password or the flag in the file. ROT10 is not standard. If it was a ROT13, CyberChef would have actually picked it up. So now looking, it loads a fake password. It reads, it loads the real password, reads it in, checks it with the user input, asks user input, checks it, writes it, and based on result, writes either the flag with the user input and not the password. That's why we couldn't fake the if statement in the debugger. Or it writes the I said you can't see me. So basic how I work with reversing. It gets more complex the moment you get more functions, etc. And there's a lot of anti-reversing tricks, but you mostly see those in Windows files. They are really good at those. Linux is really easy.
Circling back to the, you jump to, hey, this is a ROT operation. Basically, a ROT or a Caesar cipher is that when you add a value to something that you know to get another value, and then when you want to decipher it, you subtract the value, and you get something that you have encrypted. And so what we see here is that nonsensical list of characters that we saw, those bytes for which one was even unprintable, is actually a string that if you modify it by adding 10 to the character that is being used, you actually get a different value, a decoded value.
And you actually get whoops, you did see me flag.
Maybe we could show that in CyberChef.
I'll do you even better one in a sec.
Oh, you're probably going to pull out VI again, aren't you?
Yes. Why? You know what? I will open it up. I'll open up a Python script in Mousepad. I mean, I'm going to go neutral grounds
YOLO.
I'm going to go neutral grounds here. I'll open up a Python script that shows how it's encoded and how we can decode it. So, Ghidra. Ghidra, really good open source reverse engineering tool. It's getting more and more mature every release. Other options. I'm going to skip on Radare Cutter because I have no experience with them. Those are text-based. Cutter is the UI. Radare is a text-based reverse engineering tool. I have no real experience with them. There's IDA, and it comes in freeware and in commercial. This is the freeware version. The commercial version is expensive is an understatement, and I'm used to expensive tooling as a programmer. It it is limited to. It doesn't come. The free version doesn't come with a decompiler, so we only have assembly. I still use it a lot. I heard somebody say, "Oh, this tree looks really like the IDA view." The IDA by default uses the control flow view. You can turn it off, but IDA is quite good at it, and IDA has a different disassembler than Ghidra, and it appears, or no, it's actually the case. There are multiple interpretations of binary operations depending on the disassembler. I had projects where IDA picked up the correct bytes and Ghidra just joked on it and had the weirdest bytes. There's another reversing tool that I will show after this, Binary Ninja, which has yet another disassembler. I actually use them side by side to double check the code, because they sometimes really differ. 1 byte off means that the byte code is completely different. Means that the assembler structures are completely different. Ghidra's main strength, UI, it's really fluent. It has a really. It got better in Ghidra, but yeah, the structural flow graphs are just really strong, and it's where you work in. Where in Ghidra, you actually have to open it up, and you don't work in it. And it has better detection mechanisms. For example, the main function here is already recognized. Let's see. Yeah, that's IDA. Free version, limited in functionality, no decompiler, and limited in platforms it supports. And then there's an other one. Oh, I always make that mistake of pressing Ctrl Q. And I'm getting a dry throat. My apologies. Then a third tool that just came out with the new version. It's commercial. I need to say that. It's a lot cheaper than IDA. IDA is a lot of zeros, depending on what you want. There's Binary Ninja, which currently is my personal tool of choice. It's not free and has a lot of restrictions when using the demo. You can use it for 25 minutes before it quits. You can't save anything, and you can't use plugins. But with the latest version, let's go disassembly graph, main, also better support for signatures. Same principle as IDA, but this is the disassembly. It also supports a low-level intermediate language, so pseudocode, which is annotated assembly with data types, data sizes. Medium level goes a bit more towards C, but still assembly. Or still uses registers, etc. High level, sort of pseudo C, but if you look here, data typing, etc., is really confusing. And since 2 weeks ago, when they came out with 3.0, they have pseudo C, which is actually quite good. This for me is really easy to read because I'm really used to reading C. And you can also go to linear. It's another option. I think it's $300. I'm not going to recommend it. I would actually recommend Ghidra if you're starting out, just because it's free. But have a look, and if you really like it, you can always decide to invest in IDA or Binary Ninja or whatever. So, reverse engineering tools. Then, as promised, rounding off.
In mousepad. Yeah.
Oh yeah, I wasn't allowed to type VI. Okay, sorry. You know what? We have the system handler designed. Yeah.
Oh yeah, that's not totally okay. Fair enough.
Mousepad. Okay.
Mousepad. Can you zoom it in a little bit?
Yes. So, small Python script. What this is? These are the hexadecimal values. I actually fixed the endianness for this. I could have used struct to unpack it, etc. But I thought, let's do this. And what this one does is we have a range of bytes. It prints the decoded version. Then it loops over all the bytes and adds 10 to the value. And then it prints the decoded version. So let's run that and see what it gives. Indeed, this value that we had, if we would have had added 10 to everything, we would have had a flag.
Nice. Shall we also show it in CyberChef for the people that are not very familiar with Python at the moment?
Yes, let's do that.
CyberChef is awesome. It is one of the tools that I wholeheartedly tell people to go and learn.
If you don't, if you play CTFs and don't use CyberChef, what are you doing? I mean, it is
doing it
it's
manually,
the best.
probably. Yeah, it is wonderful. You can even do the hex string that you found in Ghidra or in the disassembler. But yeah, you currently have.
And you can also change the endianness, etc. But this is a standard Caesar cipher, ROT 13. I didn't know if they had a full ROT.
Yeah, just drag it to the right, the ROT 13.
Oh yeah,
it has.
It's a ROT 10. No. Yeah, but it's little endian. Let's extract LSB. No, that's literally the LSB. Let's change the endianness. No,
I wouldn't do that. First, let's just convert it from the text.
Oh yeah, I forgot the. It's okay. First, no, because it's not because it's character based. The original, okay. Small background, ROT 13, also called the Caesar cipher, cipher, as in Julius Caesar or Augustus Caesar, is one of the first forms of cryptography that they had, where they took a letter and added a number into it. It only works. The original Caesar cipher or ROT only works on letters on the alphabet. It doesn't work on ASCII values. So the actual version would be that we dump it to hex.
No, you can just. I see what you mean. Yeah, that's why I always use the bytes. Indeed. So now you go to hex and then you do the from hex and do the comparison. That's what you mean.
Yes. And then the ROT, can we actually? I don't know if we can.
You should do the rotate lowercase, rotate uppercase, and rotate numbers.
Okay.
Oh, this is quite interesting. This is a really cool demo effect thingy, right?
Well, I never. Yeah, it's not a full ROT, so I didn't know if that's why I wrote a Python script instead of used CyberChef. So I'm learning on the fly as well. I mean,
but if you toss in the bytes and then rotate the bytes.
Okay, then we also immediately fix the endianness. Yes. Okay. Oh, we still had it open the mousepad, didn't we?
Yes, because that's a very cool tool that you use constantly instead of something that you close all the time. Anyway,
No, I
Idefix,
normally don't close it all the time because I run Tmux, but that's a different story.
Idefix asks, with the +10, can you also do a Stack Overflow or underflow with the preparing part? In this case,
No,
I don't think so. No.
no. What you start, you can't. Theoretically, it would lead to numeral overflow or an int overflow, which is not the case because it pushes out a bit pattern. We're actually working on bits and not on bytes. And they just get concatenated. So we can't overflow with this. You can use the bit, yeah. Okay, you could create an integer overflow theoretically, but it's not really relevant because it's read as text, not as an integer.
Yeah. It's
So
also
and it's so it's not a signed integer. Then you could or an unsigned, and then you could int overflow it. But yeah, it's read
the
as
buffer
text.
also
So,
limits it to 21 characters, right?
yeah,
21 bytes.
yeah,
So it's hard to do anything. So you cannot overflow anything because it reads the maximum amount that is allowed in the buffer. So the buffer will always be 21. Even if
yeah,
you give it 6,000 characters, it will just read 21 bytes.
yeah. If it's and that has also to do with the C call it's made. If it's a gets, then it would actually overflow the buffer, and then we could first overflow it into the stack and later into the heap, depending on the layout. So, you wanted this?
Yeah. So we have hex. So we do the from hex thing. So we toss away all these things.
Okay, I'm learning here about how you want to do a rotten bytes. So tell me.
So I'm just winging it right now because I
Yeah,
did
yeah,
not
me too.
prepare this.
I'm
So, but my thinking is the add is
add to
the
input to the
given
given.
key.
Yeah, that's a
Increase,
mod.
is there an increase?
Yeah. So there's a lot, and I mean a
Yeah,
lot of things that they do.
maybe a plus. Is that plus?
4.
Ah. No, that will not work. That will not work. But if you have a hex string, we can have the from hex. It will take the hex and will create a
Yep.
string from that. Um,
And this auto delimiter, well, this takes a
yeah,
lot.
it works beautifully. And the
Yep.
lot itself does not work here, right?
No, rod
Because
does not work because a rod only works on alphanumeric values.
yeah, and so, because the yeah, so the bytes
And
are
this is
out
a
of the range. Yeah,
and this is actually a byte addition and not a rod.
yeah, it has to be possible. It has to be possible.
Okay. So,
But I
if
don't
you
know
want to talk
how
about
at the
rabbit
moment.
holes, welcome.
Yes.
Welcome to the rabbit
Well,
hole of let's figure out how CyberChef works because we don't know.
yeah.
I'm actually gonna read. In the meanwhile, I'm gonna read Discord. I don't have YouTube open, so I don't see the chat there. And let's see if
There's
there's
no
any
comments there.
questions.
Yeah.
I think speedrun for the win. Oh, I don't think we speedran this
Nah,
version.
it was that was a remark when we quickly glanced over IDA.
Ah, okay. Yep. CTFL would also try to change the jump 0 to jump not 0 after the compare and then execute it. Yeah, but it won't give the flag in this case. That's why I didn't do it. I was thinking about including binary patching and manipulating E flags, but it wouldn't give us anything in this case. Other session. I'm gladly going into binary patching and E flags. Runtime manipulation of E flags. Scrolling back.
Oh,
So you have a solution yet? Have you solved it?
No, I'm scrolling still, but Sursiak says it's about 25 minutes, so you have to do a speed run of the.
Yeah. Well, on
I will
selling
figure it
Binary
out.
Ninja, well, you shouldn't buy it and absolutely go Ghidra SRE because it's really good tool. The plugin environment for Binary Ninja and the plugin community is really good. It's really good. And I actually bought it. So I'm biased. I think
Yeah.
that's it in terms of questions. Unless you have solved
People
the...
can ask questions in the chat as well, in the voice chat and on Discord while we are busy there, of course. So that's.
Okay, I'm seeing a wait until he figures out that Emacs has a full hex editor. No, I will never figure that out.
It is very true. It is very true.
No,
No.
I mean, I'm also not cheating by using NeoVim and then going after Emacs. I'm just using Vim. Let's be clear.
Yeah,
Let's
you're
keep it
not
fair.
VI, but you're FIM, right?
I'm using Vim. Yeah. I actually, my first programming job at a client, that was Java in '98. So Java was really, really new. Was at a client, and I got to work, and I had to work on a Solaris Spark Station
Uh-huh.
with VI as editor. VI, not Vim. I prefer Vim over VI. But yes, it is doable. I actually programmed in VI a long time ago.
Oh yeah, that I did as well. It's wait, I think I have it. X41 from X. It's quite funny because when I moved to United States back in '98, I
I like
got a job.
Pyro's screenshot the best. If you search Google on Emacs, it's first thing it says, did you mean VI?
Yeah, and if you search on VI, it says, "Did you mean Emacs?" Yeah, because it's a holy war. So
Yes. I mean, let's talk
let's
brazier placement next.
yeah, but maybe while we do that, 6D5E, right? That's the 6DX5E. Right? Yeah.
Okay. Or you go to Discord and I dump the string.
Oh yeah, beautiful, beautiful, beautiful. Wait. I think I.
Is this the point that you start sharing your screen? Because I'm just reading chat and nobody can see what's happening.
Yeah, beautiful. Yeah, I need to. I have figured it out. Wait.
Okay. Stop
Yes.
screen. All up
Share
to you.
screen. Yes. So Ghidra, no Ghidra. Listen to me. Cyber Chef is awesome. Awesome.
Agreed.
Awesome. Let's move. I need to move a screen to another window. There we go. Resize it a little bit. There we go. It is nicely now. Right, there we go. Now I need to
it is
zoom
add.
in.
Okay.
Yeah,
It is.
it is add. It is. So when you have a list of bytes, like we had from the program, you can do a from hex. And from hex will take each byte and put it into an internal representation. I don't know what the exact value is, but converts hexadecimal byte string back to its raw value. So
ASCII table.
Yep. Yeah. So and then you can do an add, and on add you can take a value. It adds the input with the given key. So we can, for instance, say 10 decimal, add that to this thing. And when it does that, it will take it and put it into the ASCII version of it. Now the question becomes swap endianness, maybe.
No, but this one was already fixed. The endianness was already fixed on this one.
But if you have the original, so you copy it from
It's the word length is 2 bytes in this case, by the way. It's with ELF, it's a 2-byte word length.
Very good. But then you would get it will swap it. So if you take the original string or the original set of bytes, you put them in CyberChef, then you can do a swap endianness. So it will put the endianness correctly. Then it will do the from hex. So it takes it and puts it into the raw value. And then you can do an add 10 to it. So, and if we talk about fourth generation programming languages, CyberChef is basically your fourth generation programming language, right? You have blocks and you don't know what it does, but it actually, you can stack it. So it is awesome. Awesome.
Yes. A lot of things to say. You can have a lot of opinions on what GACQ does, but they make awesome tools.
Well, same as with the well, I don't know,
NSA.
that little company called the NSA.
Yeah, absolutely. I mean, that the tooling is really good. So
Okay,
that was my presentation, actually,
very cool. Very cool. There,
including CyberChef rabbit hole.
Yay! Well, not a complete rabbit hole. It only took like a minute or 5 to figure out. Yeah, nice. Very cool. Well done. We have had a lot of work up to this point to get a reverse engineering introduction into the world. Hopefully, for the people following along, it was doable to follow along. So, congratulations. Thank you very much for doing this.
My pleasure. Was fun.
We shall close the live stream and move back into Discord so that we can chat with people. We have Cookie's Choice still to do, of course.
And Cookie's Choice, I mean, if you're talking hack the box sweaters, absolutely go for it.
Well, you cannot get this one. This is a Novi exclusive. But yeah, I have the Santa sweater, which is quite nice. You saw it with Ian Austin talk. And the hoodie is so nice indeed. Yeah, we want a hoodie too. Yeah, beautiful. All right, people, have a on the live stream. We are moving back to Discord. Next month, there will not be a Discord meetup. There will be an actual meetup. I will put the invitation out there in a little bit. So be there or be square, as they would say in the 80s. Yeah. So I hope to see you all in 2 months online, maybe next month in real life. Maybe we can meet Barre and all the good people of the Discord finally for a real time and have a real drink. So
sounds good.
Yeah, let's close out the broadcast and go back to Discord. See you all later.
Thank you very much.
Bye.
Bye.